Hello and welcome to our session on the chi-squared test. Now in this test, if you think back to what we've done in our previous hypothesis tests, it's all been using quantitative variables, variables that have numbers as their scores, as their values. An issue is, what if we have nominal variables, variables that have categories instead? What do we do then? Well, the chi-square test is a good first step into exploring that kind of variable and what kind of questions we could be asking. And we're going to ask two types of questions, similar but not exactly the same. The second one arguably being a little bit more important and more commonly used in research, but the first one's a little bit easier to understand, so we'll use that as a stepping stone to the other one. The first one is called the chi-squared goodness of fit test, where we are going to observe some frequencies, or we're going to get some observations, and from that get our frequencies. For example, let's look at different kinds of attachment styles people could have, and the different outcomes, the different possible outcomes we're looking at are secure, anxious, and an avoidant attachment style. So we observe some frequencies from a survey that we do, and we get that 45 people had a secure attachment style, 26 anxious, and 19 an avoidant style. And we want to ask, does that fit with the general expected distribution of attachment styles? Now, based on external research done prior to this study, we, for example, know that 56% of people in general have a secure attachment style, 20 an anxious one, and 24% an avoidant one. Our basic question is, how good does this observed survey result fit with the general public? So what we're going to do is we're going to see, well, based on our 90, if we add these up, my pen doesn't want to stop moving. That's okay. I understand, pen. There we go. I add those up and I get 90 people in my survey. I want to then ask myself, well, what do I expect if this fit with the general public? And it's not actually different for this specific group of people. Let's suppose a specific demographic or a specific location. I want to see if that's different from, or significantly different from, the general expected distribution. How good does the observed distribution fit with the expected distribution? So if there is no difference at all, then I expect 56% of my 90 people to have a secure attachment. 20% of my 90 people that I survey to have an anxious attachment style, and 24% an avoidant attachment style. So I get these expected frequencies. And I'm going to compare that to the observed frequencies that I observed from my people. The statistic that we're going to calculate is this chi-squared statistic. And what I'm going to do is, these are my observed numbers, And I'm going to compare that to the expected numbers by taking the difference of each, so the 45 versus the expected 50.4. Square that so that positive and negative differences, it could be higher or lower, don't have a cancellation effect. And I'm going to take that as proportion to the expected. And I'm going to do that for each of the three, like the calculation shows here. And we're going to keep calculating that. And then we're going to get our chi-squared statistic. That is going to be what I use in a comparison distribution. Now, the comparison distribution I'm going to show you here depends on my degrees of freedom, which will be the number of categories that I have minus 1. But I use it in the same way as I did the F distribution. There's a mathematical formula behind this, which we're of course not going to show for the sake of simplicity, this being an introduction. So let's just see what did we get, just roughly, and then we're going to go through the hypothesis testing a little bit more carefully. I get a 4.45. So I would look at my degrees of freedom in this case is 2, because I have 3 categories, minus 1 is 2. So I would look at my 4.45, and that would be my observed chi-squared. But of course I have to compare that to a cutoff. Now, depending on the alpha level, the confidence level that I want, and the degrees of freedom, I have a chi-squared table that I can look it up. Now, because of the 2 dimensions of this, just like for the F distribution, not everything is listed, only the commonly used alpha values. So in our book here, this is on page, whoops, too far, 679. We have a little chi-squared cutoff table here. So 2 degrees of freedom. Let's go for an alpha of 5%. And I'm looking at this 5.992. That's my cutoff. So let's write it here. Cutoff 5.992. Observed was, what did I say? 4.45. 4.45. And I see the cutoff, or the observed rather, is not past the cutoff line. So we consider the evidence to not be extreme enough, or not qualified to be called extreme, and it fits within the expected variation from one group of people to the next. I'm not going to get the exact expected numbers. There's going to be some fluctuation, some variance, of course, but this chi-squared statistic tells me when is the fluctuation so extreme that it's possibly because the group that I'm surveying is actually different from the general expected group. So if we look at this in terms of the more structured hypothesis testing procedure, we have 2 populations, people like the students I'm surveying, and then the general public. And my null hypothesis is that the distribution is the same. So we are investigating how good our observed distribution fits. It's a little noisy outside. How good our observed distribution fits to the general expected frequency distribution. Goodness of fit test. And then, of course, our research hypothesis is that they are different. So then we look at our chi-square distribution, 2 degrees of freedom, 1 less than the number of categories. And we're going to use an alpha of 5%. With those degrees of freedom, we saw in our table that our cutoff line was at 5.992. We calculated our observed chi-square statistic, comparing the observed to the expected, got 4.45. We visualized it, and we make our conclusion that we do not reject the null hypothesis. The evidence isn't strong enough to suggest that the people that I'm surveying, I'm investigating, is different from the general public. So that's going to be the first question that we investigate, the goodness of fit observation versus expected frequency. All right. I'm going to actually be right back and just close the doors to minimize the sound. And we are back. We are back. So let's look at another example just to make sure we understand the procedure through calculating our chi-squared statistic, where we get the observed frequencies that's given in a question, or we do a survey ourselves. Compare that, or we have to know our expected frequencies from a prior study or some external knowledge. Then we look at the difference between the two for each of those categories, square them, which is quite common, and then divide by the expected frequency every time, and then add them up. So let's see an example that is different but the same kind of situation. So we have 300 students at some university. They attended a political demonstration. With regard to the year in school, are these students significantly different from students at this university in general, based on prior rallies or demonstration attendance? And we're using a 1% alpha this time just to mix it up. So we get our observed frequencies and compare that to the expected frequency. So we observed 30 freshmen, 20, 90, 120, and 40 graduates for a total of 300. And in general, we expect these percentages to attend. Now we have 1, 2, 3, 4, 5 categories in our variable, so our degrees of freedom will be 4, 1 less. So let's set this up before we look at the calculation this time. So our two populations or two groups vary, comparing this political demonstration attendance to attendance in general. The null hypothesis is that essentially the frequency distributions are the same, or within some expected fluctuation, versus research hypothesis, no, this one's actually different from what we expect. So we have our degrees of freedom there. We want to perhaps first determine what will be our chi-squared cutoff in our distribution. Well, we have a 1% alpha and 4 degrees of freedom. Let's go have a look. 4 degrees of freedom, 1% alpha will be 13.227. So we remember that. And now we have to go and calculate. So what does that calculation look like? Well, we have to calculate the expected frequency based on the percentage and the total. 15% of 300 is 45, and when we calculate the expected frequencies for each of the categories. And now we want to see, well, yes, 30 is different from 45, 20 different from 45. Oh, this 90 is exactly what we expected. But overall, how different is different enough? So we take the difference observed minus expected for each one, square that, and in each case divide by the expected to get a total 32.22. That is our chi-squared statistic. Here, let's write that down. Chi-squared statistic. And we compared it to the 13.227. Clearly our observed chi-squared statistic is much more. And we can then say the evidence is strong enough to suggest that this is actually very different. We reject the null hypothesis in favor of the research hypothesis. Those students attending political demonstrations have a different distribution in terms of year in school than students at the university in general. So in this case, I guess I misspoke a little bit. I mean, the wording in the question could clarify exactly what we're looking at here. I think the issue initially was students who attend the political the demonstration, are they distributed differently than the students in the university? So it's quite simple in comparison to calculations that we've done before, and the logic behind the chi-squared statistic, the graph, the table, the cutoff versus observed. It's all should be all very familiar. So let's see where we're at here. This was our conclusion. Great. But unfortunately, it doesn't stop there. This is arguably the more commonly used chi-square test. But it's very similar to what we've done before, except that we have multiple categories, or multiple kinds of categories. In a sense, we have a contingency table. For example, we are investigating young married women who have children versus those who do not have children and either rent or own their home. So we have two variables that we're comparing to see if they are independent of each other. So this is the chi-square test for independence. So we're asking, essentially, does having children affect renting or owning? Or the other way around, does renting or owning affect having children? Or are these two variables independent? These two are nominal, categorical variables, which is where the chi-squared test comes in. But the question is how? So if we look at this table over here, we have a total number of people in the have children category of 16, no children 24, for a total of 40. So this is the total number of people. So we look at the percentages for the total number of people having children. That's 16 out of 40. That's 40%. And the other row, the ones not having children, that's 60%. And then we ask ourselves, well, if renting or owning is independent from having children, then in the rent column, we expect a 40-60 breakdown. Again, in the owning column, we should get very close to a 40-60 split again. But if these numbers in each column are very different, that could give us evidence that renting has an effect, some effect on having children, yes or no. Owning your home has an effect, some having children, yes or no. We don't know what the effect is, but we're trying to see if the evidence suggests that these variables are not independent. Okay, so that is the idea here. So what we're going to do is something very similar. Within these cells, these are the observed numbers, right? The observed frequencies, and the rest is just totals and percentages. So we're going to take our total look at our rent column, 25 people there. We expect the having children number to be 40% of that 25, in other words, 10. We expect, so this is sort of now what we expect, without looking at renting or owning, just sort of the first variable only is what we expect. We expect in the rent column to have 60% be not having children. So we expect numbers of 10 and 15. We didn't get them. Is that significantly different or just normal expected fluctuation? That's the question. And then in the owning column, we have the same issue. We expect a 60-40 split from the total of 15 people in that column. That should be 6 and 9. Not quite what we got. And then within these bold numbers, this is observed versus our expected numbers. We're going to do something very similar. We're going to take the difference here, observed minus expected, so we'll have 4 of them. And then the calculation is very similar to what we've seen before. So we use the totals to get the expected numbers for each cell. And then the chi-square statistic is exactly the same. In this case, we have 4 of them. We're going to do it 4 times. The degrees of freedom, I don't know if I say it down here, the degrees of freedom in this case is a little different. Number of columns minus 1, number of rows minus 1. So in this case, degrees of freedom is only 1 because I had 2 and 2. 1 times 1 is 1. So we get a chi-square statistic and degrees of freedom. We need that for our table to look up. We get 11.05. So let's see what is the detailed hypothesis testing structure. So our null hypothesis is that the two populations are the same or independent, that one variable is independent from the other variable. And then, of course, the research hypothesis is that it's not independent. So we're assuming the null hypothesis is true, then we should get these expected numbers, compare that to what we observe. The chi-square statistic is a measure of that deviation, that fluctuation. And if that is big enough, the fluctuations are big enough to be more than just coincidence. So we set up, okay, our chi-square distribution, 1 degree of freedom. Let's go look it up. Where do we find this? If we use an alpha of 5% with that degree of freedom, look at our table. It's over here, same table, 5%, 1 degree of freedom, 3.841. 3.841 is our cutoff. We just calculated an 11.05. That is much more than the cutoff. So we reject the null hypothesis in favor of the research hypothesis and conclude that the evidence is strong enough to suggest that these variables are not independent. Among young married women, renting or owning is not independent of having children. We don't know what the effect is, but there is some relationship between these two. So this comes in where we have a nominal variable with categories and not a quantitative variable where we can calculate a correlation coefficient. Other kinds of variables require other kinds of tests. So this is the chi-squared test for independence, but it's very similar. And we should be able to easily pick out which is which based on how many variables we have. In the very first one, we had one variable and some external knowledge for what the expected distribution is. In this one, we have two variables that we are trying to investigate if they are independent of each other. So running through the steps here briefly, we determine the actual observed frequencies that will most likely be given to us in a question in some form. Determine the expected frequencies based on the row percentages, and then calculate the expected frequencies and compare that to the observed, and then everything from this point on is the same in terms of calculating the chi-squared statistic. Let's have another example just to emphasize what is different and also what is the same as the first chi-squared version. So we have here a study of for the college experience of students who were the first generation in their family to attend college. These students were compared to other students who were not the first generation in their family. So let's have a look at actually what is observed here. Oops, I don't want to show too much. Let's just show the table. Now, a lot of things are going on there. We don't have it all in the beginning, but we have these observed numbers. So first generation or not versus if the students dropped out or not. And we observed 73, 89, 657, 1226. For example, 1,226 students in our survey were not first generation and did not drop out. Okay, so let's go back to what we're actually asking here, students surveyed and students in general. We are looking at the null. I like to look at the null hypothesis maybe first and then work this back. We're trying to investigate if the two variables are the same, if dropping out is independent from being first generation or not. And then the research hypothesis is that it's not independent. So we have a chi-squared test for independence situation. We have two categories in each. I don't think this is not right. This is not right. Let's update this. There's a little typo there. If we look at the table, sorry, that's not my table. My tabs keep moving. Tab, stop moving. That's the one I'm looking for. Whoops, don't show too much. No, leave something to be desired. We have two variables, two categories for one variable, two categories for the other variable. I'll write it over here. Degrees of freedom is therefore 2 minus 1 times 2 minus 1 for, again, a 1. Okay. So this will be a 1, but I guess for a different reason that was written there. Now we need to look up for an alpha of 1%, let's say this time. What is the cutoff chi-squared score? Well, 1 degree of freedom, alpha of 1%, 6.635. That's where we get this 6.635. Now we need to calculate our chi-squared statistic. So let's do that. Not showing too much. Let's just show the table first because there's still work to be done on the table. A lot of things sort of filled in here. Originally, I only have the 73, 657, 89, 1226. I calculate all these totals. And then I look at I ignore the column variable and just look. Dropped out is 162 out of the 2045. That's 7.9%. So this is our expected percentages, if you will. I expect 92.1% of people to not drop out if I completely disregard the generation of going to college, first generation or not. So then I go to each column and say, if in the first generation column I had 730 people, I expect 7.9% of them to drop out. That's this one over here. So let's write that over there. 7.9% of 73 is, no, sorry, not 73, 730 rather. The total is 57.7. And that's where this comes from. I expect 92.1% of people to not drop out. So 92.1% of the first generation column, and I get my expected frequency. Then I go to the other column, and I do the same thing. If under the null hypothesis, it didn't matter, the column doesn't matter, I expect 7.9% and 92.1% every column. So I calculate the numbers I expect, and then these ones in the blue shaded cells, the observed versus expected, those are the ones I use to calculate my chi-squared statistic, where I look at observed minus expected squared divided by expected every time for 4 of them. Add them up, however much detail you need, 6.73. I can then go back. And remember, you can, of course, always pause the video if you need to read it more carefully. What did I just say? 6.73. So it's close. It is close. But it is more than our cutoff. We therefore reject. That's why we have a cutoff, to make a clear decision, yes or no. In this case, yes, we reject the null hypothesis in favor of the research hypothesis. The evidence is strong enough at a 1% confidence, at a 99% confidence level, that these two variables are not independent of each other. I reject the null hypothesis. Null hypothesis says they're independent of each other. Our evidence says no. Those gaps between observed and expected is just a little too big for this to just be random coincidence. First generation students are somewhat more likely to drop out during their first semester than other students. Now, this lack of independence, or this dependency, doesn't mean one affects the other, same as the correlation issue. It doesn't imply causation. It just says they are related to each other somehow. So that is hopefully a solid introduction to the basics of the chi-squared tests. There are 2 of them, very closely related. The first one, the goodness of fit test, if I want to, for a single nominal categorical variable, compare if the observed frequency distribution fits a general known or expected frequency distribution, so just one variable. And the second chi-square test for independence of these kinds of variables. When I'm comparing two, they don't have to have the same number of categories. It doesn't have to be 2 and 2, but I'm comparing the observed and the expected frequency to decide if these two variables are independent of each other. All right, that wraps up this session. Until next time.